Hey everybody, the mighty Pacific Ocean at the coast of Washington, welcome. We're near the towns of Ocean Shores and Pacific Beach, just right over there. We're talking about earthquakes today and the risk of tsunami coming in and crashing on these shores as tsunami have done many, many times in our geologic past. There's a magnitude 9 earthquake waiting to happen 60 miles offshore here, and there's real concern about tsunami coming in here along this coastline. For this program, I think we should go and look at some physical evidence that we have that magnitude 9 earthquakes have happened in the past right here in Washington, and then talk about a geodetic network. The PANGA lab from Central Washington University has installed GPS receivers across the Pacific Northwest to monitor what the crust is doing tectonically, but also the purpose of those GPS receivers is to help mitigate emergency problems in the precious minutes and hours after the next big earthquake at this coastline. So we're going to combine real geology evidence in the ground with planning for the future and concerns about emergencies coming down the road here at the Pacific Northwest and especially the Washington coast. So let's start with some real geologic evidence in the ground at the coast. What would that look like if we're looking for evidence of a deadly tsunami hundreds of years ago? USGS field geologist Brian Atwater went looking in the 1980s and found convincing field evidence deep in a ghost forest. Working up a sweat here on the banks of the Copalis River, southwest Washington. This is a big deal. I really want to make sure you've got the significance of this. We're at the Ghost Forest. We've paddled up 30 minutes from Copalis Beach, the town, to get to this spot. And Brian Atwater did the same thing back in the 1980s, looking for evidence of a possible major tsunami that came washing in on the Washington coast at some point in the past. Because back in the 1980s, nobody really bought the idea that magnitude 9 earthquakes were possible offshore. Now everybody believes it. Everybody is sure magnitude 9 earthquakes have happened in the past, and most recently, everybody is sure geologically that on the night of January 26, 1700, at 9 p.m. local time, in the dark, this tsunami came in. The evidence is right here. This is what Atwater calls a 3-layer cake. There's different colors here, right? There's kind of this chocolate brown mud up high, and there's a gray sand layer, and then below it is some black mud. Atwater expected the mud. This is an estuary after all. But the excitement here is the gray sand. It shouldn't be here. The sand was swept here by surges of tsunami waves on that terrifying winter night more than 300 years ago. The trees here were also victims that night. The magnitude 9 earthquake offshore dropped this land 5 feet in the blink of an eye, plunging the trees' roots into the tidal zone. Dead trees poisoned by salt water. There's not many people that are bright enough and astute enough geologically to tell a major story from an exposure like this, but Brian's one of those guys. So when nobody believed magnitude 9s were possible, and nobody believed there were major tsunami that really had come in on the Washington coast, he used this exposure to convince people. And there are older sand layers that record older tsunami here, with an average of 500 years between quakes. With Atwater's convincing evidence for repeated magnitude 9 quakes, a plate tectonic model emerged. Magnitude 9 earthquakes around the globe strike coastal regions where a subducting oceanic plate locks up with the overriding plate. After centuries of stress, the pent-up energy suddenly releases. The land at the coast suddenly drops, and the ocean floor shifts, producing a great tsunami. Now that alone would be enough for most folks to worry about, but Washington and Oregon citizens must also face future likely earthquakes on newly discovered shallow faults, inland, in the Puget Sound, Willamette Valley, and even the deserts east of the Cascade Range. These inland shallow faults don't create magnitude 9 events with tsunami. But these quakes are big enough to kill thousands of residents potentially. In response to our growing awareness of the extreme tectonic hazards we face living in the beautiful Pacific Northwest, the Geology Department at Central Washington University began installing permanent instruments across the Pacific Northwest to measure tiny movements in the crust and to better understand the mechanics of Pacific Northwest earthquakes. The Pacific Northwest Geodetic Array, known as PANGA, is a network of 350 continuously operating, high-precision GPS receivers installed all across the Pacific Northwest. Snoqualmie Pass, Interstate 90. We're at Hyack, right where they park the snowplows. And right behind the DOT shed, we've got one of our GPS receivers anchored right into the bedrock up here at Snoqualmie Pass. This guy is solid into the rock. Drilled, all 3 legs and the steel rod that's beneath the instrument, drilled right into the bedrock and anchored hard with some concrete. These GPS receivers calculate their position by precisely timing the signals sent by GPS satellites high above the Earth. GPS simply boils down to triangulation, the old technique used by land surveyors long ago. But with GPS, the measurements are continuous and extremely precise. The Geodesy lab at Central Washington University is run by Tim Melbourne.
Okay, so we are up here on the roof of Lind Hall, which is the home of CWU's Geological Sciences Department. And the data pours into this building within a half a second, no matter which receiver you're talking about. So yeah, obviously it would make sense that Lind Hall can get to Lind Hall within a half a second, but it's less obvious that a station out on the coast of Washington or the coast of Oregon or up on Mount Rainier or Mount St. Helens can also get here in a half a second, but in fact they do, and we use a variety of different telemetry systems, from the mundane like cell modems to very complicated one like dedicated satellite telemetry. But in any event, the data all pours in here, and then we actually take those measurements, and we actually have to do a bunch of analysis of the measurements to get the position of the middle of one of these antennas. What we actually bring into the building here is the transmitted message and the carrier phase from the satellites, and we get it in here, and then we run fairly complex computer algorithms on them to estimate the position through time. So what we do is we come up here and we will take out and temporarily, to test what we're doing, put a receiver on a table and then slide it around. And we slide it around with a ruler and a compass so we know exactly how much we've displaced an antenna. And then we actually measure it and make sure with the GPS and make sure that what we're measuring from space is identical to what we know we're measuring things by. But that's the key thing to remember, is as we slide this, we're measuring it from space, and it doesn't matter whether it's the roof of Lind Hall or out on the coast of Washington. If a receiver moves 5 centimeters, we can see it.
The Geodesy Laboratory at Central Washington University serves as a data analysis center. Measurements from the PANGA instruments are augmented by using additional GPS receivers that comprise the Plate Boundary Observatory, operated by the U.S. National Science Foundation. The systems administrator for PANGA is Craig Scrivener.
PANGA is doing 2 kinds of processing. One of them is in this machine off on the left, which is doing daily processing. And that means that it's getting data from across the Pacific Northwest once a day, and then doing processing where we can take into account a number of optimizations that let us get down to millimeter precision in the solutions that we produce for each of the stations. Then the newer approach that's being taken is something called real-time GPS, and this set of servers is involved in that kind of processing. The idea here is to get solutions that are on the order of every 1 second or every 5 seconds. So they're nowhere near as precise as the daily processing, which was down at a millimeter level. This is more like centimeter level precision. But the advantage of this is that we can start using it for things like seismic hazard and response after a major event.
Major events mean magnitude 9 earthquakes that planet Earth has produced 4 times since 1960. Chile, Alaska, Sumatra, and most recently, Japan. The Tohoku earthquake and killer tsunami struck on the afternoon of March 11th, 2011, and for the first time in history, a dense network of GPS receivers recorded the dramatic effects of the quake. Within seconds after the initial unlocking of the subduction zone, land at Japan's coast, including GPS instruments, lurched 15 feet seaward and dropped 5 feet. And there's a direct correlation between the offshore underwater earthquakes and the size of the tsunami. Magnitude 7 earthquake offshore, no tsunami hazard. Magnitude 8 offshore, localized, relatively low tsunami waves. But a magnitude 9 earthquake offshore means a major tsunami with waves of water greater than 100 feet high and surging miles inland.
The GPS network comes into play really for the biggest earthquakes. We have had for 50 years seismic networks full of seismometers that are exquisitely sensitive. Like the best instruments in the best locations can measure velocities in tens to hundreds of nanometers per second. And so the seismic networks typically run into trouble differentiating between the sizes of big earthquakes, the difference between a 7.5 and an 8, or an 8 and a 9. And that's due to the physics of the problem and the way the faults actually radiate the energy. So the GPS comes into play at that high-end scale. It's trivial for the GPS network, and assuming you can keep the power on to your stations, the telemetry going, the processing going. When you have a magnitude 9 earthquake off the coast of your state, there's just no way the coastal regions isn't going to move many meters. Okay, if you have a magnitude 8 or say a 7.5, you expect well under a meter of motions. And so, if something were to happen where we see 500 miles of the coast of Washington and Oregon move 5 or 6 meters, the entire coastal region, and we see that in 2 minutes, we know we have a very high 8 or a low 9 on our hands. If all the seismic alarms go off and it turns out just a very small area, say 30 kilometers, has moved a meter, we know that's not a magnitude 9. We know that's probably not even an 8. It's probably a mid-7. And so the GPS really is complementary to the seismic monitoring that's been around for several decades. But it comes into play only for the biggest earthquakes.
Because there's a lot of noise in the network now, you'll have these spurious signals where things will move around. But the idea is with large earthquakes like what happened in 2011 in Japan, the motions are so large they overwhelm all noise sources, and everything will move as one coherent unit. And having the real-time data streams available this way is the best way to visualize this.
We developed a software package to plot GPS data in a meaningful manner in real time so that we can define thresholds for automatic warning systems. Also, it includes modeling so that we can delineate regions of increased risk during an earthquake or a tsunami, which is important to not only the scientific researchers, but emergency planning officials and first responders. The toolkit also is really comprehensive in that it includes site photos, site information. You can plot time series, graph fault displacements at depth, and mapping surface displacements.
PANGA's network of receivers is dedicated to monitoring movement in the Earth's crust. But there are other uses for the data.
A couple of these are fairly high profile. State Route 99, the Alaska Way Viaduct, is a 6-lane mega freeway through downtown Seattle, and that was damaged in the Nisqually earthquake in 2001. And since 2001, well, in the years following the earthquake, the bridge actually subsided by 10 centimeters into the kind of the loose soil out there, and that's actually a source of worry. And so in cooperation with the Department of Transportation, we've put 3 of these receivers out on the viaduct itself, and we measure that thing essentially once a second, 24/7, and we can measure it to a few millimeters accuracy. And so from a operations and forecasting and response standpoint for the Department of Transportation, this is incredibly useful, because the alternative is to shut the freeway down and go out there with surveying crews, and they do this still a few times a year, but that requires a complete shutdown of the bridge, and you only get a few measurements a year. Here you're getting a measurement every second.
I can't think of a better place to look for evidence that earthquake research in Washington is taking root, is taking hold in public policy in Western Washington. I think if Brian Atwater had not done his landmark work out at the coast, perhaps people wouldn't have taken this structure's integrity as seriously as they are now. As Pacific Northwest residents continue to prepare for earthquakes in the next century and beyond, Central Washington University's PANGA lab has now become an important source of information. The network of GPS receivers monitor our crust around the clock, and when that next magnitude 9 quake strikes off of our coast, emergency officials within seconds will benefit from instant information to help get aid to those needing it. Earthquake research in Washington, a work in progress with preparations to come.
Funding for this series is made possible in part by the Donna J. and Charles T. Cole Charitable Foundation and by the Department of Geological Sciences at Central Washington University.